This is the second video introducing the idea of atoms. So atoms, what they do is what they can do, and what we're used to them doing as humans, paying attention to, all of the things that make up our surroundings. These atoms, they group together, they network together. In some cases, they form very rigid networks that look like crystals, but sometimes they just group together in gases or liquids forms, and they make these materials. And the idea is, for example, atoms, in particular hydrogen and oxygen atoms, if you get a whole bunch of these things together, they can first form a situation of a water molecule, and then from that, they can make a material that is like bath water or water in a lake, right? Yeah, so these atoms, they group up and they make these materials, and the idea is the materials are made out of these atoms and nothing else. Like there is nothing else in there, just these atoms, right? There's a very special word called elemental, and elemental materials are a material with only one type of atom. So for example, a material with only one type of atom is a collection of hydrogen gas. And hydrogen gas is a situation where hydrogen atoms actually pair up and they make H2 gas molecules. And then you just have a bunch of them together, right? So each of these dots is meant to represent individual hydrogen gas molecules. And together, they are a substance or a material known as a hydrogen gas. And the same thing with helium. It's interesting, though, that helium doesn't pair up with other helium atoms. Helium is known as a noble gas atom or noble gas element, and each helium atom is perfectly happy to remain unattached and solo. They're very noble. So you can have a helium gas, and the principal pieces of the helium gas are individual helium atoms. So you probably know this, but most materials are not elemental, right? For example, is made out of many different kinds of atoms. Glass, silicon is in there, but so is oxygen. Plastic, lots of carbons and hydrogens, maybe some nitrogens. Air has hydrogen gas in it. It has nitrogen gas in it. It has oxygen gas. It has ozone. It has many different things. It's got H2O in it, right? It's got water up in there. Humid air is very watery air. It's got lots of things. It's got argon. Argon is a type of atom that's up in the atmosphere, like Earth's atmosphere in particular. And then water, definitely not elemental, right? Water molecules are actually little groupings of two different kinds of atoms, so it's not elemental, right? And steel is also not elemental. Steel has some iron in it, some chromium, some molybdenum, various different types of atoms. So the notion of the elemental material was a really big idea long ago when people were essentially early scientists. Some of them were element or atom hunters, and they were looking for an element that nobody else had ever seen, right? So it's kind of like searching for very novel materials. And this is early careful chemistry. So as they were discovering more and more different types of these elemental substances, They were noticing a periodicity or a organization or pattern. They noticed this pattern in the chemical properties, as well as some other properties, but the chemical properties of the elements that they knew of. And there was this person long ago named Mendeleev, a Russian scientist, who, amongst other people, were trying to figure out this pattern, which is what physicists do, right? Physicists and chemists and other scientists are looking for what are all of the patterns in nature and how do you use them to make predictions. And a really interesting set of predictions that people were doing is they could say, based on the organization of the chart, they could describe the qualities or the properties of stuff that people should be able to find, but the hunters hadn't found them yet. Mendeleev, brilliant guy, famously a very, very good teacher. And I think this is pretty cool, but each of these elements are labeled with what's called an atomic number. And this atomic number is equal to the number of protons in the nucleus of the particular kind of atom. So this is called the proton number or the atomic number. And if you go look at atomic number 101 on this periodic table of elements, it's named for Mendeleev, right? Atomic number 101. And I think this is pretty cool because in college courses, when you take the course, say Math 101 or Chemistry 101, these tend to be the first course in a series where you're actually learning the material, right? First in-depth look. And I don't know if people did this on purpose. I kind of hope they did, or I'd like to think that they did. But giving Mendeleev Element 101, he was the ultimate teacher, and he gave us the ultimate organized chart of elemental materials. Or in a sense, he gave us the organization, actually. After Mendeleev, these element hunters still had to go and find things that Mendeleev's periodized chart was predicting. Okay, so moving on in this introduction to atoms. So atoms make up materials. And interestingly, what's got to be happening, if you look at how atoms, here, let's say this is an atom and this is another atom, right? If these two atoms tend to group together and sort of like try to remain next to each other, to have some common sort of spatial association, what they need to do is they kind of have to have this kind of like equilibrium sort of distance between them. And in order to maintain that, these atoms, they need to push away from each other if they're too close, and they need to attract each other if they get too far apart, so that they tend to want to stay together, right? This tendency. And this tendency, which definitely happens between certain types of atoms, right? It doesn't happen between every atom. For example, two helium atoms, I mentioned helium before, they could care less if they were next to each other. They're perfectly satisfied being solo. But for example, if you had the situation of an H, another H, and an oxygen, the way that these connect up is to make a little molecule known as a water molecule, and it's each of the hydrogen atoms and the oxygen atom likes to stand at a certain distance. And if some process in nature, if some other thing comes up and bumps into the water molecule, right, it might bump into it pretty hard and push the hydrogen atom towards the oxygen, but the hydrogen and the oxygen in the molecule repel each other so that the hydrogen can't get very close to the oxygen. But then when the hydrogen is pushed away and runs away or accelerates away under the influence of that force, it actually can't get very far away because in some sense this little molecular bond, or actually it's a bond between atoms. That little bond is kind of like this little spring that's really hard to change the distance of. But these particular repulsions and particular attractions for various different kinds of atomic combinations and arrangements, they are what give rise to the structural details of the material, like how rigid is it? Like diamond is very rigid, can scratch glass. Or what's the density of it? Like lead. Lead is a very dense material in the sense that you can have a very small volume of lead, but it will be very, very massive. These details of how the atoms like to sit next to each other also is going to have something to do with what they look like. What color are they? Also, whether or not they're clear, right? Whether or not visible colored light can go through them. Also, they'll inform how they break or shatter or just cleave or fall apart. It's also going to tell us about the boiling temperature, right? How hot does the, like what temperature does it need to be in order to change from the solid into the liquid state? It's also going to inform what kind of chemistry the materials take part in, whether or not they behave as acids, for example. And also they're going to determine electrical properties, like whether or not the material would make a good wire, right? And the people who make tons and tons of money because they're really smart with this kind of way of thinking about stuff, they make tons of money designing drugs, being good chemists and designing, good paints or processes to make novel fabrics, right? Materials engineers might be trying to design materials that can be used in computers or cell phones, right? Cell phone screens, for example, or a new sort of novel, like using titanium to make body parts, right? New joints for people, hip joints or knee joints, right? So all of these issues, right? These kinds of scientists and engineers, they make a lot of money because they know how to understand enough about materials and elemental issues to make interesting products. All right. So as an example of thinking about atoms and materials, let's think about solids for a moment. So in solids, the individual atoms, they have relative locations that are fixed. That is, if I have a little grouping of atoms that are in a solid, and this atom is called A, and this one is B and C, D, E, and F, right? If they're in a solid, then the atom A is not going to slide past E and go to the other side of F, right? So A can't do that in a solid. It can do it in a liquid and it can do it in a gas, but not in a solid, right? So let me erase that possibility. So they have fixed relative locations. But what's really interesting in solids, liquids, and gases, but in solids in this example, is none of the atoms are actually stationary. They are sitting there vibrating back and forth, up and down, and they're also rotating in place. They're very vibrant. And in fact, actually, this is what's meant by temperature, or it's related to temperature strongly. The higher the temperature, the crazier is this atomic motion in a material. So I'll finish with some really interesting issues that arise in thinking about materials a little bit further, and you're going to read about them in your chapter readings. The first issue is the notion of an ion. So let me actually add some space. Okay, so atoms are ions when the number of electrons is different from the number of protons. So the number of electrons might be designated like this, and the number of protons might be designated like this. And if you do this, like you take the number of protons and you subtract the number of electrons, this is so-called the ion charge. So as a very simple example, let me look at my periodic table of elements here. You can hear me shuffling pages in my book. For fun, let's take sodium. So sodium has an atomic symbol that looks like this. It's Na for sodium, right? And this is the atomic symbol. And sodium has an atomic number of 11. So 11, right? What this means is that the number of protons equals 11. And what sodium can do is sodium can lose an electron. So that means if it loses an electron, it used to have the same number of electrons as it did protons. So the number of electrons used to be 11, but if you lose one, then it's 10 instead. And then back over here, if we want to get this ion charge, then we take the number of protons, which is 11, and we subtract off the number of electrons, which is 10, and we get 1. That is, sodium tends to make the ion sodium plus 1, where this plus 1 is this ion charge. Isotopes is a different kind of concept. Atoms can have different isotopes, right? So an atom of a particular elemental material will always have the same number of protons in the nucleus. Remember, the nucleus is where the protons and the neutrons live. And the number of protons is what designates the type of atom we're talking about. But atoms can have different isotopes, and different isotopes they'll all have the same number of protons, but they will not have the same number of neutrons. So that means the same type of atom, that is, it will have the same atomic symbol, like for example, capital C is the atomic symbol for carbon, and carbon has it as atomic number 6, right? So carbon is a 6-proton atom, so the number of protons is 6, but there can be an isotope of carbon that has the number of neutrons equal to 6, but we can have another isotope where the number of neutrons is equal to, for example, 7, right? And these are different isotopes of carbon. Both of these isotopes have the same number of protons, which is 6. But these isotopes, what makes them different isotopes of carbon is the fact that one has 6 neutrons and the other has 7 neutrons. So the last sort of list of special words in talking about atoms, I've actually already brought up the idea of the molecule, like for example, the H2O molecule. So it's literally a little grouping of an oxygen and two hydrogens that form this little system or entity, right? And if you have many of these molecules, you can have water, right? A material like water. And these molecules, if the water is very cold, they form up into crystals that give rise to ice. And if the water is a little bit warmer, you can have the liquid version of water. And if the water is even warmer, you can have the steam version of water, right? Or the gaseous. Yeah, so that's the idea of the molecule. It's this sort of little grouping of atoms that kind of gives rise to the main chemical properties of the material or the substance. Mixtures are just like, for example, the air in our atmosphere is a mixture. It's a mixture of, for example, argon gas, hydrogen gas, nitrogen gas, gaseous water, or actually water vapor, right, in our air. And it's a mixture in the sense that these things, they're all present in air, but they are not chemically interacting, right? Yeah. And then compounds, for example, you can have materials referred to as ionic compounds and salt, like salt in the ocean, table salt that you put on your French fries. Sometimes one of the particular salts that people talk about a lot is called sodium chloride. And sodium chloride is sodium ions and chlorine ions, right? Remember that sodium forms the plus ion and chlorine actually forms the negative ion. It's got more electrons than protons. And these two things, they are oppositely charged, and so they attract each other, right? So that so many sodium ions and chlorine ions can get together and make a little crystal of salt that you can consume that tastes nice on French fries. There is a type of matter called antimatter. It absolutely, positively has positive mass. There's no such thing as negative mass, right? So gravity is only ever attractive, and you only ever have positive masses. So even antimatter versions of materials have positive mass and is attracted to other mass. What makes antimatter is sort of a very interesting and strange thing that nature has in it. For all of our particles, like electrons and protons, there is an antimatter version. This one is called the positron, for example, and the antimatter version of the proton, you could just call it the antiproton, right? Yeah, so this is a pretty interesting thing. In nature, though, there are many more of the matter versions of these particles than the antimatter versions of the particles. And asking the question, why is there more matter than antimatter is a very interesting question to ask, and people are still working on the answer to that. The very last topic in this introduction to atoms is dark matter. And dark matter is a very mysterious material that people do not know what it is, but it's a very serious scientific endeavor, or a scientific question, to figure out what is this dark matter. People know that it needs to exist, but people don't know what it is, right? So I'll leave it at that, but it's an open science problem, science question. Astronomers see the evidence that there must be more material in the universe, So they see evidence for more material, but they don't actually see the material itself. So it's referred to as dark matter. Okay, thank you.